Today we are going to talk about something that happens in every blast furnace at some point, the low stock line. But more importantly, we are going to talk about what happens after it drops. We all know that a low stock line is a problem, but the real challenge is not just spotting the deviation. It's about understanding the thermal deficit it creates and precisely calculating how to fix it before it cool down the hearth. My goal today is to walk you through the physics behind these and then give you a clear, logical framework for calculating the exact compensation you need. To do that, we first have to go back to the basics of how the furnace actually work. So, the physics of a stockline deviation. So let's start with the physics. We call this first section the physics of a stockline deviation. It's crucial to remember that the stockline is not just a number we track, it's the boundary that defines our processing volume. When that boundary drops, the entire thermodynamics machine of the furnace is thrown off balance. We need to understand why before we can understand how to fix it. So let's dive into what exactly or what actually changes when that level drops. So the here we will see the role of processing height. So as you can see, the diagram of a furnace cross section showing the gas residence time arrows shortening as the stock line drops. These highlight the top gas temperature and indirect reduction zones also. So take a look at the diagram on the left. Here is the normal stock line level. Now imagine it drops down to here. Suddenly three critical things are compromised. First, the gas residence time. The rising gas has less distance to travel to the top, so it spends less time transferring its heat to the descending burden. We are basically shortening the heat exchange zone. Now coming to the second area, which is about the thermal preparation. Because the gas escape faster, we see higher top gas temperature. Think about that. That's the energy literally leaving the furnace. Energy that should have been used to melt iron. And third, chemical preparation. The shorter contact time directly hinders the indirect reduction zone. That's the efficient reaction where carbon monoxide pulls oxygen out of the iron ore. So that happens when we lose that processing height. We create a specific kind of problem called a thermal deficit. So thermal deficit mechanism, as you can see in visual, three block of icon, that is one is energy loss, the second is direct reduction shift, and third is the heart chilling or coldness of the heart. So let's break down this deficit. It happens in three stages. Energy loss: for every meter we drop the stock line, the top gas temperature can rise by anywhere from 50 to 100 degrees Celsius. That's the first wave of loss. Then because we have lost that indirect reduction zone, the furnace is forced to compensate with direct reduction down in the hearth, and this is highly endothermic reaction, meaning it consumes heat instead of producing it. So it's a less efficient, more energy hungry way to make iron. The cumulative effect is hearth coldness, or the more aggressive and adverse remark is wording is the heart chilling. So the heat deficit travels down to the tuyer level and we see the results in our final product: lower hot metal temperature and lower silicon level. So we have identified the problem. Now let's move on to how we calculate the solution. So in section 2, calculation logic and metric, as you can see, this is a section header with a calculator or formula icon. Uh, so we know a low stock line costs us thermal energy, but in control room we do not think in BTU or joules. We think in kilograms of coke. Operators have developed empirical constant over decades of experience. They are based on the simple logic. How deep was the deviation and how long did it last? So these constants are our starting point. So let's look at the specific metrics we use. So as this shows the correction factor table, a clean table with 3 rows, parameter 1.0 deviation, average correction plus 10 to 15 kg per ton hot metal coke parameter, 10 degrees centigrade rise in top temperature, average correction is 1.5 to 2.5 kg per ton hot metal, coke parameter 0.01 drop in eta CO, average correction 3.5 kg per ton hot metal. So this table is our reference. It's our cheat sheet for quantifying the damage. For a sustained 1 meter deviation, we need to add roughly 10 to 15 kilogram of coke per ton of hot metal. If you see the top gas temperature rise by 10 degrees, that's another 1.5 to 2.5 kilogram of compensation. And if the gas utilization efficiency eta CO drop by just 1% or 0.01, that's a 3.5 kilogram hit. So these are our building blocks for calculation. But to get the full picture, we need to combine these factors into a single dynamic equation that account for time. So the total compensation formula, the formula C is equal to K multiplied by delta Stockline into delta Tk is equal to empirical coke rate increase, that is Kg uh, mm, of coke increase, delta SL where is the depth deficit in meters, T is equal to time at low level hours. So this is where it all comes together. The total extra coke required, C, is a function of three things. First, K, our empirical factor. Think of this as the penalty rate, often around 5 kilogram per meter per hour. Second, delta SL, the depth deficit. How many meters are we below the target? And third, T, the time, how many hours did we stay at that low level? So the beauty of this is that it scales linearly. A deep deviation for a short time might require the same compensation as a shallow deviation for a long time. So it's about the total thermal volume we lost. This might still feel a little abstract. So let's make it concrete with a real world example. So, uh, um, so as we can see, this is a sort of a almost just information, general information, which will be carried forward further in the other slides, which are subsequently following. So as we can see that worked example where the condition in previous slide it was shown. Depth deficit is 4.5 meter from 1.5 meter, that is 3 meter hourly deficit. So what will be the compensation? That is compensation will be 3 meter multiplied by 10 kg per meter hour, that is 30 kg per hour. So total compensation 30 kg hour into 3 hours multiplied by 200 ton hot metal per hour is the fuel that is getting supplemented. So 18,000 kg, that is 18 ton. So step 1 is the calculate the depth deficit. If our target stock line is 4.5 meter, but we are operating at 1.5 meter, so we have 3 meter deviation or 3 meter deficit. So step 2 is calculating the total deficit per hour using a K factor of 10 kilogram per meter per hour. For this severity, we multiply 3 meter by 10, that gives 30 kilogram of coke per hour for every ton of hot metal we produce. So finally step 3, if this lasted for 3 hours and our furnace produces 200 tons of hot metal per hour, the math is clear. The 30 kilogram times 3 hours times 200 ton. So that's 18 ton of extra coke. That's a significant number. But how do we get that coke into the furnace efficiently or effectively? It's not just about adding more coke. It's about how we add it. So the coke blank a philosophy that we need to keep in mind while adding. So the cook blank delivery. So as we can see that so this is the cook blank delivery method. We don't just spread this extra cook evenly across the top. That would be inefficient or ineffective. We place it a central charge. Why? Because putting that extra coke right in the center helps maintain permeability and lifts the cohesive zone back up to where it belongs. So the key is immediate execution. We need to chart this as soon as possible and as soon as the stock line is to recover. So if we wait, the thermal wave dip too low and we are already behind. And a quick warning on peripheral balance: avoid dumping excessive coke at the wall that encourages gas channeling and makes the problem worse. But before we rush to the charge all that coke, we need to consider the risk. So what is the risk mitigation? So as for the risk mitigation and warning is concerned, so a simple graphic with the three warning icon. One is overcompensation with an up arrow. Two is the gas distribution with the arrow moving to the wall. And three is the response delay with a clock. So this is a precise operation. There are three critical warning. I want to leave with you. First, overcompensation. Yes, we need to add coke, but too much leads to high silicon in the metal and high slag viscosity. That makes tapping difficult and can cause delay down the line. Second, gas distribution. Remember, low stock line often cause peripheral flow. The gas rushes to the walls when we recover the level. Our immediate priority must be things to restore that central chimney. So the coke blank helps, but we have to monitor the distribution. Third and most importantly is the response delay. The extra coke that we add at the top takes 6 to 8 hours to reach the melting zone. So this is a slow process. If you wait until you see the hot temperature drop to act, you have already missed the window. So let's bring all of this together. So coming to the key takeaways, as you can see that mm, as we wrap up, so let's look at the key takeaways. So compensation or compensate for the loss of chemical and thermal preparation volume with energy density coke before the deficit reaches the hearth. So the low stock line is not just a level on a gauge, it's a loss of volume that we rely on for chemical and thermal preparation. Our job is to see that loss, calculate its impact using the metrics we discussed and replace that missing energy with a precisely calculated coke blank before it manifests as a cold heart. It's about being proactive and not reactive.